So good morning and welcome everybody. Today's lecture is going to be on soils, the fundamentals. So we will, we've got a lot of information to cover today. It's quite interesting and probably a little bit in depth for what your average agronomist needs to know, but I'm sure you'll find it enjoyable. There's lots of info here. So we'll just move on through. So the next lecture after today will be lecture 7, soils, building what you need. And so that will be on the 21st of April. So we'll have a nice little break over the next couple of weeks and for lectures, and be back there on the 21st, starting at 10 AM. So soils, the fundamentals. So by the end of this lecture, we hope to be able to describe the components of soil, describe the different types of soil, list common Victorian soil types, so including the ones at Yanyeen, and describes common soil problems. So some of the ones that we will commonly come across will be erosion, salinity, acidity and alkalinity. And also we'll cover off why a farmer might get his soil tested and what he's looking for when he tests his soil, or when an agronomist gets a soil test done. And then later on in this afternoon's practical slides, we'll cover off getting a soil sample is not just as easy as going out and grabbing a sample with a shovel and a bucket. It's a little bit more in depth to it than that, so we'll cover that off then as well. So soil is right at the heart of a functioning society, producing something of the order of 95% of the world's food from agricultural soils. So very important, and don't ever tell anyone that's a soil scientist that, that soils aren't important, unless you want a vigorous discussion to follow. But the soil is, and I think as we all know, we have an appreciation for it. Without it, we wouldn't have a lot of what we enjoy today, especially from agriculture in terms of the food that we eat. But it offers many other things than that as well, such as filtering our water that goes down into the groundwater that we pump back up and use for it, and even just water that moves through the soil, filters that. It's also an engineering media. Obviously we build on it and we use it in building construction. But we're not focused on that today. It'll be more around the agricultural uses of soils. So the smallest component of a soil is a PED, and so the study of soil, so not dirt but soil, is called pedology. The soil is the most common natural medium for plant growth, and it's got to provide some certain properties in order to be able to provide the right environment for growing our agricultural produce. It's got to have chemical properties, physical properties, and it needs to be healthy, and we need to manage it to keep it healthy. And the properties of healthy soils is it has good soil organic matter and organic carbon, which are essential for sustaining healthy soils. And any practice, so building organic matter or inputs into the soil increases the organic carbon, and we'll find that it's these organic substances which are the smallest component but the most important. So organic carbon is part of organic matter, and all organic matter is composed of the basic building blocks made from molecules which contain carbon and hydrogen. So just think of photosynthesis and the end result of that, C6H12O6. So that's an example of a organic molecule, and that's where what plants are built from. So that's the carbon that's fixed from the atmosphere, put into plant growth organic matter, and that so that's where the carbon comes from. So here on this slide we've got it looks like heaps of stuff to take on board, but first of all, the functionality of soil, for it to function properly, and to know how it functions, it's good to understand all the different components and combinations of components that make up a soil. Typically the water, air and minerals make up 90% or more of a soil, and the rest is organic matter. So the smallest fraction is, that I was saying before, might be 5%. The remaining 5% there is going to be, as we'll understand, to be probably the most important part of that soil fraction. So air, water and minerals make up the bulk of most soils, and it's interesting, isn't it, that 25% of you, if you grab a handful of soil, 25% of it could actually be just air. Well, that's the gaps, and they're super important, those pores and the voids in that soil. The solution can fill those pores and is also vital for carrying and being able to provide nutrients to those roots. So, so just on those pictures on the right-hand side there, we've just got some a root hair and the soil particles. So this is the key for this larger picture here, which is out of the Ag Guide, which is one of the prescribed books for this course. We can see here's a root that's growing through the soil. We've got a sand particle here, and just to appreciate the size of these particles as well, we've got your humus and clay minerals. So these ones over here, we've got a void and some water in there, and we've got a nematode. And I think the main thing to take from this is that it's a complex little area, this soil, and there's more to it than just dirt. So hence we call it soil, and generally get offended if anyone calls it dirt, because they are totally different things really. And I think the other thing that bugs a lot of soil scientists when you say that soil is dirt is dirt is associated with unclean or unhealthy, and soil is actually very healthy, very clean, and very valuable for us. So just to recap, air, water and minerals make up the bulk of most soils, and depending on their location or depth, organic type substances make up the rest. Texture is describing the composition of the soil, and so we'll move on to that in a minute. And the structure describes how soil is held together. So we'll cover off those in a little bit to come. But Australian soils are described by 14 different soil orders, and can be further split right down into family, giving rise to millions of specific soil types. So we'll just move into that. So that'll be in a couple of slides' time. The next thing we're just going to have a look at is this organic fraction that we're talking about. So this the smallest component of the organic fraction, what it does, or what can that actually, what does that consist of? So just take into account this column here, the approximate biomass, kilograms of dry weight per hectare, of this organic fraction of soils. And so just think of this in a hectare area, so 100 metres by 100 metres of soil in area, and just going down into the top part of it, where these organisms exist. 25 to 50 kilograms of earthworms, and we've got something in the order of 500 to 750 kilograms of bacteria. So just to put it into perspective of what we've got there in that, making up that organic fraction. So basically organic molecules, anything that's living or plant derived. So this is just useful to think of, for discussions we might have later on in our practice session. So just describing soil texture. So this is our soil texture triangle, and it's got the most soils Australian soils comprise of three main components, and it's made up of a percentage of clay, percentage of silt, and a percentage of sand. Now, just to appreciate these all have different sizes, and how the different components of them put together is what we call the, depending on whatever proportion they're in, will give us our soil texture. So, for example, a silty loam might have in the order of 70% silt, 30% sand, and maybe 10% clay. Something like that in a silty loam. Whereas a silt will be even a higher proportion of silt and less of the others. So that's how we determine the texture using the soil texture triangle. And just given the different proportions, you can imagine will give different PEDs or different pedology and the way they are structured together, which we'll cover that off soon. But you'll be able to imagine or get an appreciation for how much sort of spaces or pores can actually be in those and can give us between those particles, and can give us a difference in how much porosity and how much water infiltration can actually get into those areas. So if they're really small, tight pores, then it's going to be, it's going to take longer for those pores, or, it'd be harder for the water to come in and out of that, as opposed to, think of a sand in these, because they're big particles. They'll have big gaps between them, so the water can come in and out relatively quickly. So the difference in sizes of these, of course, sand is 0.2 to 2 millimetres, fine sand 0.02 to 0.2, silt is down to 0.02 millimetres, and a clay is 0.002 millimetres. So to put those into perspective for you, if you, for example, get a particle of sand and drop that into some water, a sand particle will drop through 100 mil depth of water in a second, whereas a silt particle will take 5 minutes to drop that same distance. Whereas a fine clay particle, they are so fine that it would actually take 860 years drop that same distance. So they're hugely different in size, and so just getting appreciation for the different combinations of those particles gives us our different soil texture. So I'll just make sure there's no other points there that I had. Yeah, so as agronomists, it's important to know things like sand particles are relatively inert, and they don't bind together or hold nutrients, not that well anyway. They need a fair bit of organic matter to actually hold them together. So that's mainly because our sands are large in size, and they can be blown, and water can rip in and rip out. So they do drain well, but they can actually also often repel water. Clay particles, on the other hand, are very reactive, and they can be quite different depending on the parent material they were derived from. But one of the more important things is they have a negative charge on their surfaces. And so this is what your positive cations and your nutrients can attach to and be retained for extraction by the plant roots. And they're probably the main points. And as we increase organic matter and humus into the soil, that can also increase those little positively charged sites, or what we call cation exchange sites. And we'll discuss that in a little bit more detail a bit later as well. So moving on to soil structure, this is the way in which particles are arranged and bound together. It's so there's a few different main types. So singular grain PEDs, blocky PEDs. We can have a platy structure. We can have a granular structure, lots of granules, or a prismatic type structure. So the PED is a primary soil particle, and an aggregate is where several PEDs are stuck together. So that could be sand, silt and clay bound together, or that could be all sand PEDs, or that could be all silt, and so this will obviously give us our texture that we were talking about before, but how they're stuck together will give us our structure. And that will also determine the voids or the air spaces or pores in between them as well. And they're super important for holding the air and allowing for air and water, which are super important for the roots. So a physical fertile soil contains both fine and large pores, and they can even have cracks that continue down to the subsoil. We'll learn a bit more about horizons in a minute. But mainly, water can move easily into and through the profile. And there's plenty of water held in the pores available for uptake by plants. But there's also, it's not saturated though, it's got air there as well. And seedlings can push their way through without any trouble. So sometimes some structures are not that ideal if there's too much of, or if there's not enough pores and the structure isn't so good, then seedlings can't push their way through. But a physically fertile soil doesn't have any impediments to plant roots. So plant roots can easily grow through and explore the soil for soil and nutrients. So the soil profile, so when we look at a horizon, such as, you know, when you look at the sunset or rise, we're looking at a horizontal or relatively flat lines. This is similar to the soil. It's in layers, relatively flat layers. There can be a little bit of undulation up and down, but these flat layers are what we call horizons, and depending on what country you live in, there's some some areas have more horizons than others, but mainly in Australia, we sort of split it between the A and B horizons. You might find in some, there might be a highly, so if we have a look at this little picture down here, in some sort of, like the O horizon is a very rich organic matter horizon. Generally in our cropping soils, it doesn't get a chance to build up. It's and a lot of our soils actually don't have such a horizon. Australia's soils are very ancient soils and very weathered, and so it's common for us. It's easy for us to just to have our split between our couple of different horizons there, and we can further segregate those horizons dependent on the different components that we can see. But sometimes you can't actually see them, but they can be measured. And so we'll talk a bit more about that as we go on. But mainly the A horizon is the topsoil where the bulk of the soil nutrients are located. That's where the roots will grow and extract nutrients and moisture. And it's commonly where most of our agricultural fields start. So, as I was saying before, we've got 14, we've classified our Australian soils into 14 orders. And I guess it's probably the main ones that we'll come across in our agricultural soils are the ones with a strong texture, so there's a contrast between the A and B, or they don't have a contrast between the A and B. So it's these ones here. These other ones are more commonly, you'll find them out in the desert or other parts of Australia, but they're human-made, or they're not in the arid zone, but in agricultural soils, these are the ones. And there are actually, apologies, there are a couple of ones here. The ones with the stars are the ones that we'll mainly come across in our soils used for agriculture, but predominantly you'll find that all of these ones with a strong texture or laxer texture between A and B are the ones that we'll be dealing with. What else have we got? So the ferrosols and dermasols are relatively closely related. However, the deep red ferrosols offer little resistance to plant growth. They can exhibit quite good structure. So some of those include our good krasnozems that we grow our potatoes on. They're a deep red, high iron, beautiful looking soils. We may have seen some of these as you travel around through some of the Tulangi or around Ballarat, places where they're growing, often referred to as good spud country. So here's some pictures of some different soil types. Typically, these aren't pictures from out at Yan Yan, but they're typical of the ones that you would find, or the same soil types that you would find out there. So we've got a sodosol, which is, you can see that's got a distinct A and B horizon, a vertisol, where it's not quite as distinct, so it lacks that, that contrast, and a tenosol, which is also lacks that contrast. You can see it can't quite, it's a bit hard to read, but this is the pink shows where these soil types commonly found, so your sodosols, your vertisols, and your tenosols. So the Yan Yan soils were classified by a Soil Science Australia expedition, which there's many soil pits out there, and so if you were to walk around the farm, you'd come across a few soil pits, and so this Soil Science Australia, so they're an organisation which you can become a member of if you would like. Just Google them. But they went across and assessed the whole farm as part of the competition, and they to see who could come up with the correct classifications, and so that's what they did, and this is what they came up with. And so the hills comprise mostly of Silurian aged sandstone and shale deposits, so they're called shallow sotosols. And these grow into the lower slopes of colluvial material, deeper sotosols, and then variously aged alluvial derived flats. So if you can just imagine being out there on the farm and just looking at those different, you know, the hills versus those lower flats, then that's the type of, you know, the soils they classified in those areas. The soils in those sort of lower areas, they had grey sotosols, and they also had so the tenasols, and the western edge of the property. They actually found some quaternary basalt flows, which gave rise to a deep black vertisol. So, and that's quite typical, that black vertisol there, cracking clay. Yeah, you can see that without looking too hard. It's very common out there at the Yan Yan farm. So I've just got a couple of descriptions here. So sotosols are soils with a strong texture between the A horizon and the sotic B horizon. And the sotic B horizon is also strongly acid. So a sotic horizon, and we'll learn more about this when we look at our reading soil tests, but that's a high sodium content, and we'll also learn that sodium is not very good for structure and not very good for helping the PEDs form in a way that allows voids and pores. In fact, it blocks all that down. They're packing that tight that yeah, there's basically no room for any air or that, and it's it's what we call a hostile environment for root growth. It's not very good at all. Vertisols, on the other hand, are clays with shrink swell properties, and that's why they can exhibit the strong cracking when they're dry, and they can crack right down at depth. Can also have what's called slicken sides, and so that's just if you they have a real. You'll notice if you've ever dug a hole or been using an implement like a crowbar or a matic and digging in these soils, and they get that real shiny sort of slicken side to them. That's just because of the structural and how they compact in. But it's yeah, just one of the properties of the vertisol. Australia actually has the greatest area and diversity of cracking soils of any country in the world, believe it or not. And finally, the tenasols. These soils are generally only weakly. They don't have weak pedologic organisation apart from the A horizons. So it's and it does encompass a rather diverse range of soils, which are widespread in many parts of Australia, but they lack that. Basically, they lack that big contrast. They look very consistent all the way through, and they can range in colours too. Pretty amazing. Pretty amazing soil. So just we can classify soils right down to there's to the family grade. So there's different levels, so 5 different levels. So we're just at the very high level at the order, at 14 different orders. It goes all the way down to the family, which can split it between acidic, dystrophic, red canter soil, thin gravelly, silt, clay, deep, and can be very specific. And a lot of this info is we probably don't really need to be that specific when as an agronomist. However, it is really good to know the properties of these soils and what we can and can't do with them. And they're probably the main take-home messages for all of this, just to understand that they are quite different. There are millions of them that you can't possibly know them all, but you can know the properties of what's really good and what to look out for. And a lot of that is what we'll talk about. But I've just got another note here. Yeah, no, I think that was for the last slide. So, yeah, so I wouldn't expect you to know or to memorise all of the orders and how they're broken down into the the different levels. But just to know those main key things about the texture, the structure, and how they're made up into profiles is probably the main points there. So now we're just going to look at some, now that we've got an understanding of soils and what makes them up, we're just going to go through and talk about some common soil problems that we'll come across, because not only may we come across them, or we could be brought into areas where, due to different practices or whatever it may be, either indirectly or directly, you might have someone else may have caused these structural problems, or it could be natural, just due to some whatever's been going on. But we'll just go through some of these issues and discuss the implications for them. So first of all, compaction. So that's an issue that can come about from, for example, excessive wheel traffic or plough layers. Often you'll find a compaction layer after paddocks that are ploughed year after year. You can also get compaction from heavy foot traffic from stock, but it's generally also in the presence of moisture. So you'll find that that some soils are fine to travel over them with heavy machinery or put lots of stock across them, but once you get a certain amount of moisture in amongst that soil profile, you'll find that it becomes more malleable, and that's when you start getting the issues. And so that's when we don't want to be working some of these soil types when they have too much moisture. And just think of a paddock that's been pugged from stock because they've had heavy foot traffic, heavy hooves pushing in and compacting areas and causing compaction, or even just traversing on country. Just think of if you go up and down your lawn, or just think of an area in the wintertime that's been passed over by cars, it becomes very compact. And so the issue comes about when there's moisture involved. And so sometimes it's not a good thing to be working soil when it's got too much moisture in it, but it can also be bad when you don't have enough moisture. So really, ideally, a soil should be filled with pores, both micro and macro pores, so different sized pores. Micro pores obviously can't be seen with the naked eye, but it's these pores that give rise to, or they're part of the structure that's really important, and by the soil disturbance, so tilling and driving across or heavy foot traffic, we can really destroy these pores and change that structure. The others macropores, so from organisms, so worms and ants and plant roots. They can help with our macropores and help combat some of this stuff. So we don't want to, we want to try and improve the infiltration rate, and these micropores and macropores are what we want. But they really affect the infiltration rate of moisture into our soils. So soil structure is so soil crusting, hard setting, slaking and dispersion are things we'll learn more about a bit later on as well. But generally, soil crusting is an issue with sodic soils, and it's very common in Northern Vic in the irrigated soils. If you can imagine, if you've seen a sodic soil, have you ever seen puddles in a paddock which have been really cloudy, and they can get so bad that just by trying to wash your hands in one of those really cloudy puddles, or just dipping your finger in, it can come out like you've dipped your finger in paint. I've seen some paddocks like this that have been worked up and they're trying to grow a crop in it, and it's just absolutely terrible. Just because it's been ruined, the organic matter's taken out, the structure's just been totally ruined. And that's typical of a sodic soil. And we'll talk about addressing that a little bit later on. But, and so we'll talk about, how we manage that, as well as erosion and salinity and acidity, alkalinity. We'll talk about those a little bit later on as well. So with that, we need to be able to determine how suitable the soil is for a given crop. And there's a number of methods for doing this. So we can sense it using chemical analysis. We can use it doing a physical handling analysis. So essentially is the physical handling, and the other is when we send our soil test off to a lab, is the chemical analysis. And so as agronomists, we'll need to be able to conduct soil tests and get the full picture. So and that's just collecting a sample, which will cover off the proper method, and we'll learn more about all of this in this afternoon's prac. And then in later pracs, we'll learn about interpretation of these results for the grower or farmer. So just a little bit more on the physical handling, or the centrally determined things there, using the senses such as your sight, your smell, your feel. So visual inspection of the soil. Because really, just by looking at the soil, you can tell a hell of a lot about it. And just think of looking at a soil pit or a soil core. You can look down there and see, first of all, the contrast, so any colour changes. So we can pick different layers out, and we can tell their likely properties. So what we're actually doing is, sometimes without even knowing it, within seconds we can have something analysed centrally, and then work out what tests we might need to do just to further refine what we're going to do, how we're going to manage this soil going forward. So soil testing is really, and we'll cover this in more detail later on the survey, but it's trying to detect and quantify the properties of the soil that we can't see or feel. Some of those soils, they don't look, as they go down through the profile, they don't look to change much. However, they can actually change chemically, and the roots can see or feel that, but we can't see or feel it. We need chemical analysis to tell us what's actually going on there, and if we need to take any remedial actions. There are also other analyses which we can do, which are important, but generally I haven't really done many of these myself out in the field, but you can detect genetic and enzyme activities. They're generally very expensive to do, I'm told, but you can pick up a range of biodiversity or enzymes that could be active there. One enzyme that springs to mind that I have done some work on is the urease enzyme, which breaks down urea and is responsible for nitrogen volatilization. You may have heard of that term before. But agronomic chemical analysis, so what we're doing is we're testing the soil solution or the ability of the soil to actually donate nutrients into that soil solution. Once in the soil solution, they're then available for plant uptake. So there are 17 known essential elements for plant growth. They're split between macro and micro nutrients. So the macros, we require them in larger amounts, and the micros, the trace elements, very small amounts. And so the macros we generally will be able to see and do recommendations for from our soil tests, whereas the micro or trace elements, we'll normally need to do tissue testing to diagnose those. The other soil tests that we can do, or the analyses as part of our soil test, we'll be looking for things like pH, the cation exchange capacity. So remember before we spoke about the negative exchange sites on those clay particles, they can hold the positive cations. And so looking at the capacity of the soil to hold onto cations. And the other one is the electrical conductivity, which is tells us the gauge on the salinity or the salts in the soil. So here's the the 17 essential nutrients or elements for plant growth. So in being essential, it means just that. So plant growth will not be possible without that element, so it's essential. So if you take that element out, plant won't grow or will show severe symptoms. So I'll just quickly run through. We've got nitrogen, phosphorus, potassium, calcium, magnesium, sulfur. They're our major elements. And then we've got our trace elements below. And these notes are up on Moodle, so you can come back through and see what those nutrients are, what they're responsible for at a later time. But they're essential. You may have heard of the law of the minimum. So it states simply that the plant yield is limited by a deficiency of any one essential element, even though the others are present in equal amounts, or if they're present in large enough quantities. Another way of thinking of it is you can only fill the bucket to the lowest hole. So each hole being a nutrient, you can't fill the bucket until each nutrient is supplied or a plug is put in that nutrient's hole. That's put in there so you can fill the bucket up. That's what will limit your yield, the availability of all of these nutrients. So agronomists need to be able to identify and predict these and put measures in place so that yield is maximised. So we only have we might have a limited resource in how much rain can grow. And so that's the only limiting factor that we want in terms of our crop or our pasture is the rainfall, which we don't have control of. All the other things, we can do tests and analyse our soil and make sure that we can maximise the efficiency of our rainfall and our use of that moisture. It'll be a real shame to know that you could have grown an extra half a tonne or a tonne of wheat per hectare if you had just addressed the nutrient. That'll be really frustrating getting to the end of the season, finding out that you had a nutrient deficiency and you could have fixed it. Whereas if you get to the end of the season and you didn't get the rain, well, but it had all the nutrients, but you didn't overdo the nutrients, then that's certainly not our fault as an agronomist. That's just the way it goes. So, so now just moving on to talk a little bit more about the cation exchange capacity. So you'll find that this is really, it's complex, but it's also really interesting, but really important. So there's 5 exchangeable cations, and they're generally shown in our soil tests as percentages of the cation exchange capacity of the soil. So, and as we've discussed, the cation exchange capacity is the total number of those negative sites on the soil particles. So cations are obviously positively charged, and they're attracted to those negative sites. And the negative sites are on those clay particles or the organic matter. And yeah, so I've covered all that pretty nicely. Cation exchange varies according to the type of soil. Humus, for example, the end product of decomposed organic matter. So that's a really, really important part of that organic matter fraction. That has the highest cation exchange capacity value because of the organic matter colloids. They have large quantities of negative charges, and so they can really attract those nutrients and hold on to them. So humus has a 2 to 5 times greater ability than clay, and up to 30 times greater than some types of clay to hold those nutrients. So very important in improving soil fertility, getting that organic matter in and broken down organic matter that contributes to the humus is super important. So you can actually increase the cation exchange capacity of a soil. The other thing is the relationship between pH and cation exchange capacity. So the soil pH is important for cation exchange capacity because as pH increases, so as it becomes less acid, the number of negative charges on colloids on the soil increases, thereby increasing the cation exchange capacity. So that's I know it's fairly complex, but the pH is determined by the number of free hydronium ions or H plus positively charged hydrogen ions in the soil, and so they can actually they can bind and cause the acidity in the soil. In a nutshell. Okay, so I just had something coming up, a virus scan. Clay has a great capacity to attract and hold the cations because of its chemical structure. It's just going through a couple of notes here. Just don't miss anything. Yeah, so all right. So the clays are naturally have a high negative surface area, negative charge on their surface. Sand, on the other hand, remember it's a much larger particle as well. It has no real electrical charge. So, and this is important for us to remember too, because so sandy soils will have a low cation exchange capacity, so they've got a low ability to hold on to these nutrients. So that's good in a way in that, you know, if you're buying nutrients to put onto the soil, it's not getting tied up or attracted and bound by the soil. It's basically readily available to plants. However, it's not going to hold on to it either, so it's just going to let it go. So a little bit of nutrient and more often is a better way to go on a sandy soil than to put on a large amount of nutrients, because it can just get lost or be leached away. So that's why organic matter is really, and sandy soils are really, they need to be managed quite differently to try and conserve that organic matter as much as possible. So not too much tillage to break up that organic matter. Any organic matter that's there, you want to try and keep it there and keep it holding the soil or the sand particles together, because they won't be able to do it themselves. So there's just some associations here with nutrients and soil particles on exchange sites. So aluminium is an important one, and so is sodium. So there are some implications there. On acidic soils, we'll often find that aluminium is quite prevalent, and so we need to increase our pH to try and change the chemistry of the aluminium and lock it up so it's not so readily available and not toxic to plants. And so you'll find that the aluminium availability and the pH, so the hydrogen ions there in the soil are connected. And then we travel right through to the other end of the spectrum, where sodium is very weakly held, but that can cause the cytotic issues that we spoke about earlier, and really are not very good for soil structure. So when the exchangeable sodium is present in quantities greater than generally about 5%, 5 or 6%, it makes the clay particles unstable, and they do what's called, you know, when they make that cloudy water that I was talking about before, the term for it is called dispersion. And dispersive soils, you just think they have very poor water holding and drainage abilities. And they that's because they just don't have a very good structure. Their pores are basically non-existent because they're filled up with all these tiny little particles. So as we go through a soil profile, so just giving you an idea of how the cation exchange capacity can actually change as you go through a soil. So this is what's called a sandy duplex soil with a sandy topsoil over a clay subsoil. So this is just showing that the sandy topsoil has a lot of organic matter, and so you'll see the cation exchange capacity is quite high in the surface soil because of that organic matter that's in there due to the plant material. And that's what's really important to conserve and hold that there, because if you take that away, there's not a hell of a lot there. And then as the organic matter drops off, the cation exchange capacity drops. And then as the clay content increases with depth, we get the cation exchange capacity increasing again. So just by looking at the cation exchange capacity, we can tell the quality of the soil that we might be dealing with, and it can give us an idea of the nutrient holding ability of that soil as well. So just a little bit more on soil acidity in southeastern Australia. It is something that you will come across, and it's very, very common here in southeastern Australia. And so you can see the red, orange and red right up the eastern seaboard there, reasonably acidic soils. So just to address soil acidity, one of the things that we'll use is calcium carbonate or lime. So limestone, naturally occurring, we dig it up out of the ground and we apply that to the soil and mix it in, and there's a chemical process that goes through which it uses up those hydrogen ions and neutralises it, and as a result increases the pH. And so generally we use tonnes of lime per hectare, and so I've just got some different lime rates here for different crops. But you can just see, get an appreciation for how much different crops require to improve pastures. We're generally in that a lot of the soils we'll be dealing with in pH done in water. And remember the different methods we've got, water or calcium chloride, but this table shows us it's in W, so that indicates pH done in water. Generally, this is the sort of range that we might find most of our soils in. This is probably the desired range we'd like them to be in. And then they're starting to get almost to alkaline. And so you'll see as you increase your pH, you require less lime. As you go down, you require more lime. And this can be based on a number of things, not only the quality of the lime is one factor to consider with how much lime you need, but obviously the pH and the cation exchange capacity. So how much of that soil, what's the ability of it, how many hydrogen ions are we going to have to displace and work on with our lime in order to change that pH. So I have, I'm just going to have a quick check. I haven't been, I've had my chat box minimised, so I haven't been checking any chats, but I'm just seeing there's no messages there. But how's everyone going? We've been going for a little bit. I wouldn't mind a couple of minute break. Would you guys like a break, or do you want to keep going?
I don't mind either way.
All right, we'll just have a look. We're about 3/4, bit over it. Yeah, definitely past halfway anyhow.
Yeah, might as well just get it done. Get through.
Okay, no worries. We'll keep going. So lime is ground limestone, naturally occurring and completely made up of calcium carbonate. So naturally occurs in Australia, and there are limestone quarries which farmers purchase their lime from. Generally, the natural deposits of limestones are found near the coast. There's also another one, an important one. It's called dolomitic limestone or dolomite, and that has a high magnesium content. And generally the percentage of the magnesium in there is sort of 15-20%, and that's you know, some limes will have a low, might have 2% magnesium, but that won't make them a dolomitic limestone. They need a significant proportion of magnesium in there, and they're really handy. Not only does it work just like a normal lime, but if you've got a magnesium deficiency, then you can use it to effectively supply your magnesium. And anecdotally, there's also been some reports of farmers saying that the incidence of grass tetany, which is a relationship between it's a hypomagnesic animal disease, which causes the death of mainly big old fat cows. They're just not being nasty there. They're generally just the older, big fat cows which can't mobilise nutrients out of their fats. They're the ones that generally go down with this disease. Yes, some farmers have reported that by using, if you're going to use a lime and you have, and it's quite an important one to remember, if they do have problems with this disease, then, and you're going to put on lime anyway, then may as well use the dolomite lime, and it could help with those animal conditions as well. So the effectiveness of a lime, just in general, can vary due to the particle size, so how finely ground the limestone is, because that can affect the surface area in which it can react with the soil. And you'll know that, you'll realise this once you get out and start looking at different limes, a little bit like you might have heard an old ad about oils ain't oils, well, limes ain't limes. And you really need to look at a bit more into the quality of the lime. And the effective neutralising value is a way that we can determine one or compare one lime to another, because a lime finely ground versus one that's coarsely ground, or one that's got a higher calcium carbonate content than another, a higher moisture content versus a lower moisture content, it will increase the cost of freight. So all these things need to be taken into account by the agronomist, and and know the difference between the different aspects of limes. So the effective neutralising value is different to the neutralising value, which is just the calcium carbonate content. So just to be clear, there's the neutralising value of a soil is based on your calcium carbonate content. So that's the actual, or the purity of the lime, but how effective it is, so that's the effective neutralising value, is based on how finely it's ground, the calcium carbonate content, and its moisture content. So everything that comes into play to say how how good that lime is going to be. So that's an important note, because a lot of farmers don't realise, and some agronomists out there don't realise either. You might have a lime that's got, you know, it could have 90% calcium carbonate content, so its neutralising value might be, 90%, but its effective neutralising value is the important one, and that could only be 70%. So that'll be based on, because it's got more moisture, it's not completely dried out, so you're carting a lot of excess weight. But the other thing is, the particle size, they could be quite large, and could take 10 years for it to actually dissolve and break down and react with the soil, so or longer, and so therefore will be pointless. So it won't be very effective for you. And that schematic there is just showing a soil colloid, with the negative charges and the hydrogen ions and the different cations attracted to those negative sites, and then we add the calcium carbonate or the lime, and this is the reaction that's occurring. We're getting carbon dioxide and water given off, and we're getting those hydrogen ions are taken up in these in these different carbonate and water molecules, and leaving the exchange sites to be taken up by other more valuable cations, and also at the same time increasing the pH. So I hope hope that all makes sense for you. The other thing I haven't spoken about is you can actually come across alkaline soils, they're calcareous soil types, and they often have free limestone in the soil. And so while we normally talk about increasing the pH with those, you actually don't want to increase them any further. They're already quite alkaline. So you can use really acidic type fertilizers on there, and it doesn't matter if you acidify it. So you can literally put on liquid phosphoric acid instead of granular fertilizer. So that's very corrosive, but it works a treat, and you can supply phosphorus into those calcareous soil types and slightly acidify it and bring it back into, because, you know, being too alkaline isn't the best either. We want that sweet spot that we've spoken about in terms of soil pH. Soil acidicity, that's excessive exchangeable sodium. So more than 5 or 6% in your soil test report. So that's 6%, so more than 6% sodium of your cation exchange sites. Okay, so what we can use, so sodium is one part of sodium chloride, or sodium chloride is salt. Sodium has got a positive charge on it, so it's a cation. And that one of the reasons is it can cause, because of this, its properties, its positive charge, it can cause this process called dispersion, whereby it sticks to all the clay particles and then makes them repel one another. And it can also happen by just disturbing the soil that much that the particles are that broken up and busted that excessive mechanical disturbance can also cause this dispersion. But the main factor really, and that's just a structure issue, but the major one is this excess sodium, which really just makes all the particles, they will not form a structure. In the presence of moisture, they just want to repel one another. And, you know, it blocks up the soil pores, those really important soil pores. We ameliorate it by the addition of gypsum. So the gypsum increases the electrical conductivity, suppresses the dispersion, also supplies the critical calcium, which is 2 charges of 2 positive ion charges. So it's what that means is it displaces that sodium from the exchange sites, and it binds to those exchange sites and then can bind to another clay particle, giving form to a better structure. So it helps the soil stick together. So you'll often see that if you add some gypsum to some of this water, that it will that calcium will go out and stick to the particles, and it'll be like a chain reaction whereby they'll stick together to form large enough particles that they actually precipitate and drop out, and they'll drop and you know, grab together like just like 2 arms grabbing hold of 2 different particles. That's what little calcium ions are doing, and they will just think of that on a huge scale at a micro level to form tiny little particles which no longer take 860 years to drop out of solution, but can drop out in more like minutes. So we've got a little picture here to just show, and this is one of the you know, you might be able to do this with some deionised water yourself. Get some different soils and even look for some clay and just get some tiny bits of it and put them onto a saucer, or if you've got Petri dishes, into a Petri dish, add your distilled or deionized water, and see what happens. And you can see here the highly sodic ones in number 4 here. That's, you can dip your finger in that, and it's like dipping your finger in paint. I've seen that out in the field, and they just yeah, they need a lot of attention to get them back on track. One of the biggest issues is this crusting here on the soil surface, and here's the crust here, and you might be able to see some little roots here, but it's really difficult. You know, you can go through with your seed drill, and plant your seeds in this layer, or even slightly below it. If you're a cereal, it's going to be in a bit deeper. What happens is you can irrigate, or rain can come, and it might be fluffed up and looking good at sowing. But by the time the rain comes, the moisture infiltrates, the sodium in there makes everything repel, the structure is totally disrupted, and then it all settles out and forms this layer. And little seedlings, I've seen them, I've pulled these bits of soil up and found little germinating seeds which have just stopped just before the surface because they just haven't had the energy to bust through this layer, and it's set almost like concrete. And yeah, very, very bad for germinating crops and pastures. And that's just an example of after it's dried out a bit and it starts to crack, and but that's those yeah, flat, crappy structure caused in acidic soil. So that was soil acidity and acidity. Now I'm just moving on to soil salinity. A lot of the, so salt in a nutshell, salts are the biggest weakness, and the 4 salts are so soluble. And so one of the things you can do is wash salt away. So if you're trying to ameliorate a salty area, if you can, try and improve the drainage. If you improve the drainage and get the that salty or that salt that's in the soil leached out or moved out, then that's how you get rid of salinity. So once you sort of understand that, I guess that's pretty much all you need to know about managing salty land. What happens is the water table will rise and bring with it salts, and so that's why we need deep-rooted plants to keep the moisture and stop the surface soil and the deep subsoil water table from meeting one another, because that's when the salt will come right through up to the soil surface. So generally it happens when, you know, a lot of our land is cleared. We change the deep-rooted vegetation to shallow-rooted crops and pastures, and the higher water table releases the salts that are usually locked up in the lower parts, like really deep in the soil. And so it's when they are brought up, and with it they bring the salts, and then they can retract and go back down, and the salts stay behind, and you get these saline areas which nothing likes to grow in. And so the only way really to get rid of that is to get rid of this deep soil water, lower that water table, and then all we can really do is wash the salts out of the soil to remove it. So salinity, the movement of concentration of salt in landscapes. Yeah, so as I said, it's very soluble, carried in the water. and it's a result of rising water table. And it's an increasing problem in Australian farming, and more than likely you're going to need to, or you're going to come across it in your careers. Two main types: dry land and irrigation. You can bring it. So the one we've spoken about is the dry land, and how managing the different so deeper rooted crops, changing them over to shallower rooted crops, changing that management of water use in the profile can be the result of dry land. But the other one is the irrigation. There's something we can do there. We can pump up salty water from deep below and put that onto our cropping land. So that can be another type of how we can cause salinity, and that can be another problem. Sometimes if you've got very salty water and you need to irrigate, it may be too salty to actually use. And so what we can do is what we call a shandy, and mix it with clean water if possible. Or the other option is just don't use that water. And but it's a good practice if you're using bore water and you've got issues with your lucerne or your or whatever crop you're growing. It's a good idea to get that water tested just to see how saline it is. So just measuring salinity is it's called the EC, or electrical conductivity. And look, we'll leave that. If you want to come back, if you're interested in those measurements and the decisiemens per metre and how that all works, I'll leave that slide there for you to come back and mull over at a later point. Here's just in effect a show of the effect of salinity, of how bad it can be. You can see here deeper rooted trees have obviously been removed. Water table's risen up, it's become very salty, nothing's grown there. Surface water's come through, causing erosion. And, this obviously needs a lot of management now that it's gotten to this stage. And so, you really need to put together a whole farm plan to manage these areas. So yeah, when the water is not used and deep drainage to the water table increases and the water table rises, this is how bad it can get. Yeah, there are some native plants and trees which are very effective at using this wastewater or high salt water. Yeah, and removing them reduces the capacity and leads to salinity issues. So just a reason why trees are good in our landscape and how they can help with the salinity issues. And it's mainly because of their ability to use that deep water. Which is only crops and pastures, they just don't have the ability to do that. So you need a whole farm or a catchment approach to salinity issues. If you get a chance, look up catchment management authorities. I think there's 10 in Victoria, and they're all they have, and I think I would have mentioned this in our first track. But they're well worth knowing about, and they have lots of information and provide lots of resources there for land managers in helping deal with issues like this, because at the end of the day, they're looking at improving water quality for everyone, and they can certainly be very useful, a useful resource for you in your careers on this issue. But it's all about using water more efficiently. Just check and see if there's any other points we really need to make on this that I haven't covered. I think we've covered them pretty nicely. here are just some pictures, just looking at the accelerated license soil for the action of water, wind or other means. So you can see here is, wheat crop just got just the starting of erosion happening from water runoff, just being just from the working up of the land there to sow the crop. And these are obviously really bad gully erosion events which have occurred in places which, sometimes is very difficult to, they're in natural areas and just natural phenomenon. But ideally, we want to try and conserve as many deep-rooted perennials in our landscapes as possible. I think is the main take-home message. It all starts with us managing our dry matter cover. And we've spoken a little bit about that in our classes and our prep class that we had at Yan Yean. So here's just looking at estimating ground cover. And so that's literally by that the amount of organic matter that we have covering the soil. So we have, obviously we've got bare areas and we've got areas that are covered with organic matter. And so it's really important to manage that. And you can see this looks like a soil type whereby it would be really easy to remove that, that organic matter, dry matter cover, ground cover, and that would lead to issues for land degradation caused by heavy rain events, or a wind event would blow that soil away or wash that soil away, leading to some of those issues that we just saw the pictures of. So the sort of ground cover that we aim for as a target is a minimum of 70% ground cover. So we can manage that, and the catchment management authorities have put in place measures to help land managers ensure that they don't overgraze or remove any more ground cover, any more than that 30% removal. So you want 70% or more there, because that's been shown to be enough to avoid erosion. So at this point where you've only got a few plants, so this is a 20% ground matter, ground cover example, and over here to 80%, you can see the exposure of the soil in the 20% is far more significant to the 80%. And so if you can try not to reduce it down by overgrazing, that's been shown to really help preserve the quality and avoid those soil degradation issues. An example of what the catchment management authorities have helped land managers do is provide funding for farmers to put in what's called containment areas for feeding livestock, whereby livestock are brought in and fed in containment in order to keep them off travelling around, walking around, trampling this and breaking it down, especially over that vulnerable summer period when the plants aren't growing, but they're in a dried off state where they can be broken off and kicked out of the ground or eaten and removed. And so, yeah, you can just avoid all that by putting them in a containment area. So that actually brings me to the end of all the slides and what I wanted to discuss with you. I've actually got this YouTube clip which you're more than welcome to jump on. I think it goes for a little while, this one, but it is really, it is quite interesting. And so I'm just thinking there is another one with the prac, so as well. So just check and make sure that that it is the different one before you. Anyway, if you have a look at this, we might have just some questions now, and I'll let you go through that in your free time. So have we got any questions from anyone there? But pretty much what we've covered in this lecture is just to describe what soil is. So I'll just let you bring up any questions you've got in the chat box there while I finish off the these couple of points. So describe what a soil is and how Australian soils can be described. Know some important soils terminology and know some key soil issues. So there are some of the things that we've covered, and I think I've filled in some questions here. So a couple of example questions from this lecture material. Soil and dirt are the same thing and can be used interchangeably without upsetting anyone. True or false? One's false. Multiple choice question. How many soil orders are there in Australian soils? And that was B, 14. What is the main distinguishing feature of solar soils, and possibly the first thing we look for when we are describing a soil profile? The answer is A, distinct, A and B, horizon. So I've just got a question there from Adam. So I think Janet is actually setting the exam questions, and so she will be going through the material. So anything that's on here is possibly you're going to need to know, but you know, I don't think you'll need to go into that depth to know, like if you know the A, B and C horizons, or mainly the A and B horizons, and just go through those couple of slides and some of the points there. But you know, just knowing some of the main points that we discussed, and there's 14 different soil orders, those types of things. I think that's about the depth of knowledge you need to go into. And maybe even, I can clarify with Janet, and I'll just cover off how much detail that I think you need to know, just so that she doesn't go in and give you anything too tricky there. So, do we have any more questions? Okay, well we might call it a day there.